Hello friends, welcome to another tutorial in network analysis and synthesis. We'll discuss dependent sources today. We'll talk about the introduction of dependent sources, and in the coming lectures we'll talk about the numerical problems based upon dependent sources, how to solve those networks that have dependent sources in them using Norton, Thevenin's, KCL or KVL. So let's get started. The definition of dependent sources. Now these sources can be voltage or current sources in a network that depend upon or are a function of some voltage or current in other part of the network. So the first key point here is that the dependent sources are going to be active elements, and the second key point is that they are going to be dynamic in nature, and they'll truly represent the dynamic characteristic of a network, and I'll illustrate you with suitable examples in just a few moments. When we talk about sources in a network, we know that there are two kinds of sources: voltage sources and current sources. So if we wish to study dependent sources also, these sources are again going to be classified into two categories: voltage sources and current sources. If a voltage source depends upon some voltage in the network, that will be termed as a voltage dependent voltage source, and if a voltage source depends upon some current in the network, it will be called as the current dependent voltage source. And similarly, the categorization for current sources is voltage dependent current source and current dependent current source. If that current source is dependent upon some voltage in the network, it will be termed as voltage dependent current source, and if that current source is dependent upon some current source in the network, it will be termed as the current dependent current source. And now if we look at the symbols for these, they are going to be a little different from the normal sources. A dependent source will have a symbol of a rhombus like this, and for a voltage source it will have a plus and a minus sign, and over here its value will be written. Now depending upon whether it's a voltage dependent voltage source or a current dependent voltage source, you'll find its typical value to be 2I0 or 4V0, something of this sort, because it says that this dependent voltage source has a voltage value whose magnitude is twice that of some current I0 in the network itself. And on the other hand, this voltage dependent voltage source will say that it is a voltage source with some voltage whose magnitude is 4 times the voltage V0, which will be present in the network, of course, itself. So you need to be familiar with the symbol of the voltage source, the dependent voltage source, and the dependent current source again has a rhombus like symbol, but it has an arrow in it. Can, depending upon whether it's a voltage dependent current source, it will have some values like 2I0 or 2V0, but please understand the units of this will always remain ampere, and the units of this will always remain voltage. So do not get confused if you see a 2I0 here. It does not mean that it's a current source. It simply means that the magnitude of this voltage source is twice that of the current I0 flowing in that network. So this is simply magnitude. It has got nothing to do with its units, and of course this is again magnitude only, and its units are volt and its units are current. So let's have a look at a few network examples where we find these dependent sources. For example, I've taken up this network where this is an independent voltage source, this is resistor, this is a dependent voltage source, because it has a plus minus sign here, and this is a 2 ohm resistor, this is a 3 ohm resistor, and the voltage drop across 2 ohm resistor is V0. Now why is it important to consider this voltage? Because this dependent voltage source has a magnitude of voltage which is twice that of the voltage being dropped at 2 ohm resistor. This is negative to positive, this again is negative to positive, so they are in series. Once we determine the current in this network and we find out the voltage in this network, we'll be able to replace this dependent voltage source with a certain magnitude of voltage. Now, as I mentioned earlier, the dependent sources truly depicts the nature, the dynamism of the network. For example, if this network has a variable voltage source here, so we know this voltage could change from 6 to 3 or 6 to 9 volts. Now depending upon that voltage change, there will be some change in the current also, and because of the change in the current there will be some change in the voltage drop here at 2 ohm resistor, and because of that voltage drop change, this voltage source will change its value, because its value is dependent upon the voltage of 2 ohm resistor, and the voltage of 2 ohm resistor depends upon the variable nature of this independent source. So that's how the dynamic nature of the networks are truly reflected by the dependent sources. And moreover, you could consider that if this resistor was to change, if we change this 1 ohm resistor to some other resistance, for example 10 ohm resistance, the current in this circuit will decrease. The decrease in the current will cause a decrease in the voltage drop, and thus will decrease the absolute magnitude of the voltage, dependent voltage source here. And next we take up the example of a current dependent voltage source, which is even simpler. It says that the voltage source here, how do we find that this is a voltage source? It is simple, that it is represented using a rhombus, and it has a magnitude twice of I, and I is the loop current in the network. So if we are able to find out I, we are able to find out this voltage source magnitude. So again, not to mention here, the current in this loop will depend upon a few factors, like if we change the voltage source or if we change the resistances here, so that current will also change, and this current change will cause in the change in the magnitude of the voltage source, whose magnitude is, by the way, 2I, and it will always depend upon this. So this becomes very, very important in Thevenin's and Norton's theorem also. For example, if we were to calculate the open circuit voltage here, so no current will flow, so no current will result in the elimination of this voltage source from the network if we were to find out the open circuit voltage across 5 ohm resistor. So that's how the dynamic nature of these dependent sources will help solve the questions in Thevenin's and Norton's theorem. Now let's have a quick look at a voltage dependent current source. Now see, the current source again is represented by a rhombus with an arrow in it, and we see that the magnitude of this current source is 6V ampere. So what is V here? V is the voltage at these 2 points, or in other words, the voltage across 2 ohm resistor is V, and this current source depends upon that voltage, and that voltage will change if we change this independent current source, or as a matter of fact, if we change some other resistances or 2 ohm resistor. So again, dynamic in nature is the key point. And finally, let's have a look at the current dependent current source. This again is a current source. Of course, we have two active elements. One is the independent voltage source, one is the dependent current source. Now this dependent current source further depends upon a branch current. So this is it depends upon the current in this branch. So if the current in the 6 ohm resistor branch changes, the magnitude of the current source will also change, and you should be able to comprehend what can cause the change in the current in this 6 ohm resistor branch. So if you are able to comprehend that, you should have no problem solving the questions based upon Norton's and Thevenin's theorem, or as a matter of fact KVL and KCL. And I hope this introduction to the dependent sources was of help. If you liked the video, give it a thumbs up, and you may consider subscribing to my channel. That will be a great help, and I'll see you around in the next video. Take care, have a great day ahead and a good life. Bye.